Hello everyone, hope you're all doing fine. Welcome back to another lecture on electrostatics. In the previous lecture on electrostatics, we have learned about linear charge density. And we have also discussed the electric field at a point on the line along the length of the charged rod and the electric field at a point on the line perpendicular to the length of the charged rod. And we have also seen some different cases like electric field due to an infinitely charged wire and the electric field due to a finite semi-infinite charged wire. In this video, we are going to learn about the electric field due to a charged semicircular ring and a charged circular arc, and we will also discuss the electric field at a point on the axial line of a charged ring. So yes, my name is Vijay Krishna and you are watching UpPhys channel. Let's get started. Okay, now let's look at this example. Now electric field due to a semicircular charged wire or a ring. Now we have taken a semicircular wire. I'm taking this semicircular wire as positively charged and its linear charge density is, I'm going to take this linear charge density as plus lambda because it is positively charged. Even you can take negatively charged semicircular ring also. So if you take negatively charged ring, then the direction will be opposite to the direction that we will obtain here. Okay, right. Now let us assume the radius of this semicircular wire is r. Semicircular wire is r. Now what I'm going to do is I'm going to an angle theta, and I'm going to consider a small element here. Consider a small element here, which is making an angle d theta. The length of this element is dl. I can call this element as circular arc, small arc of arc length dl. And what is the charge on this small element, which is dq? Let it be dq. From the definition of linear charge density, we have linear charge density lambda is equal to dq by dl. If I rearrange this equation, dq is equal to lambda dl. And we know the basic formula which relates the arc length, radius, and the angle, which is arc length is equal to, I'm writing here, arc length is equal to radius into angle. So instead of taking theta, I am going to take arc length as dl, as we have considered here, and its radius is r. As you go anywhere, any element, the radius is r only, and the angle that is extended for this element is d theta. Hope I made the point clear here. Now I'm going to use this relation into this equation. So lambda, what is dl? r d theta. This is the expression that I'm going to use in the further equations. Now what I'm going to do is I'm going to identify the direction of the electric field. As this is positively charged, the electric field always points away from the positive charge at the point of interest. Now let us consider the point of interest is somewhere here. This is our point of interest. This is the point where I'm going to find the electric field. Due to this semicircular ring. Okay. Now electric field due to this ring is, this arc is in this direction, which is dE. As I have taken small amount of charge, it creates only small amount of field, which is d. As we all know, electric field is a vector quantity, so it cannot be added directly. It should be added vectorially. So what I am going to do is, to simplify this thing, I am going to divide this electric field into two components. If this angle is theta, then this angle also should be theta. Now this is d, and its component along this direction would be de cos theta, and the component along this direction will be de sin theta. Hope you have understood. the resolution of this vector into two components, dE cos theta and dE sin theta. Okay, now now let us identify the limits of this semicircular ring. That we will do in the later little bit, in a minute. Okay, now what I'm going to do is I'm going to write the equation for the electric field due to this small element, which is dE is equal to k dq by r square. This small element can be considered as a point object, as a point charge. So electric field due to a point charge at a point of interest is E is equal to kq by r square. Same formula I have written for the charge dq. For the charge dq. Now, as I know dq, I'm going to replace it. K dq is nothing but lambda r d theta upon r square. Upon r square. Now this r and r will get cancelled. What do we left with? This dE is equal to k lambda by r d theta. So this is the expression for the electric field. Electric field due to this small element. Now we need to find the x component of electric field and y component of electric field. Okay, right. Now I'm going to find the x component of electric field and y component of electric field. So x component of electric field dex is equal to de cos theta, de cos theta, and we have dey is equal to de sin theta, de sin theta. I know de. This is the expression that I'm going to use. Okay, so dEx is equal to, what is dE here? K lambda by r d theta. K lambda by r d theta. We have cos theta here. I'm writing over here. Am I making everything clear here? Right? Okay. Now the same step goes here with sin theta. K lambda by r dE is nothing but k lambda by r d theta. As I have sin theta here, I'm writing sin theta. Right? Now let us find the x component and y component. To find the total x component of the entire semicircular ring, this is the expression for the x component of the electric field due to this small element. But I want the electric field due to the entire semicircular ring. To do so, what we need to do? We need to integrate. As we all know, this entire thing comes over here like X component of electric field, x component of electric field. Now what would be the limits for this angle? Angle is changing from 0 degrees to 180 degrees. 0 degrees to 180 degrees. 0 degrees here and 180 degrees here. Okay, so the angle is extended from 0 degrees. I can write 0 to pi radians, right? 0 to pi radians. So this is 0 and pi radians. 0 and pi radians. Now k is constant. K is constant. I'm taking all the constants outside of the integration. K lambda by r. Cos theta integration is sin theta. Sin theta from limits 0 to pi. 0 to pi. Now, if I substitute pi here, k lambda by r, sin pi minus sin 0. Okay, minus sin 0. It may be degrees, it may be radians. Okay, now sin pi is how much? 0. Sin 0 radians is how much? 0. 0 into anything is 0 again. So Ex is equal to 0. This is one such very good results. The x components is x component of electric field is 0. Now coming to the next step. So d e y, here also I need to do the integration as usual. The limits are from 0 to pi radians, and this entire thing will comes out to be ey. Comes out to be ey. Okay, right. So this is ey. Sorry. This is Ey. Now k lambda by r, these are the constants. I've taken all those constants outside of the integration. Now integration of sine theta is minus cos theta, which is ranging from 0 to pi. 0 to pi. Now minus I've taken outside k lambda by r cos pi. Cos pi minus cos 0. Minus cos 0. Cos pi is nothing but minus 1 and cos 0 is plus 1. Cos 0 is plus 1. Now this minus 1 plus minus is minus again, minus 1 minus 1 minus 2, minus 2 minus plus 2. Now what am I getting? 2k lambda r y component of electric field. Y component of electric field. The x component of electric field is 0, y component of electric field is 2k lambda by r. Now, if I want to find the E net electric field, which is nothing but Ex square plus Ey square, which comes out to be Ey, because Ex is 0, which comes out to be Ey, which is equal to 2k lambda by r. This is our answer. The net electric field due to a semicircular charged wire or a ring at its center. At its center. Hope the steps that I have followed is very much understandable, right? Right. Now, as I've already mentioned, there is another method. There is a common sense method to simplify this one. We don't need to do this entire analysis. We can directly jump onto this conclusion if we use this basic common sense. Okay, basic common sense of symmetry, as I can say. When you look at this, semicircular ring, it will have many tiny pieces, tiny elements of charges, right? So, like I have considered the element here, this entire analysis is done. The conclusions have been drawn. Okay, the derivation is over, the formula is obtained, everything is clear. Okay, but I want to make little bit simpler when it comes to this entire derivation. Okay, by using basic common sense of symmetry. Okay, now like this element, we also have the element somewhere here, right? Somewhere here, and this element also causing the electric field in this direction, right? And its components, if this angle is theta, then this angle also will be theta, and this dE cos theta component goes here and dE sin theta component comes here, right? Now as this dE cos theta and dE cos theta are opposite to each other, they will be cancelling out and giving x component, I mean electric field along x direction 0. Electric field along x direction 0. When it comes to the y components, all the dE components, if you take any of the element, all the dE components will come to this direction, so they are adding up. They are adding up, giving the net electric field in the y direction, which is also considered as the net electric field at this center of the semicircular charged wire. Okay, by using this symmetry only, we have drawn this conclusion. Electric field along x direction is 0 because the components are getting cancelled. The components along x-axis are cancelled out. The only component that are being added up is dE sin theta, which are along the y-axis, So we have got the electric field along y-axis. However, the net electric field is 2k lambda by r. This result is also important, and this result is also important. This result is obviously important. Okay, hope the entire analysis is clear to you. Okay, right, let's move on to the next case. Okay, now let us find the electric field due to a circular charged arc of wire. In the earlier case, we have considered semicircular charged wire, but in this case, it's a general case. In this case, I have considered a circular arc of angle, let's say alpha. Let's say of angle alpha. Okay, I'm taking it as alpha. Now, if the entire angle is alpha, this angle will be alpha by 2. Alpha by 2. Now, what I am going to consider is this circular arc is positively charged whose linear charge density is lambda plus lambda I am taking to represent the wire is positively charged. Positively charged. Now, in the like in the earlier case, I'm going to divide this entire circular arc of ring, circular arc of a ring into tiny pieces. Now what I'm going to do is I'm going to consider a tiny piece. I came to an angle theta. I came to an angle theta, and I've considered a small element. A small element. I've considered a small element of length dl and charge dq and angle d theta. D theta. Okay, small element that I have considered whose arc length is small. A small arc length is dl. The charge on that tiny arc is dq, and this d theta is the angle extended by the small arc. Small arc, small element. Okay, now, let us recollect the definition and the formula of the linear charge density, which we have already discussed in the earlier classes in this lesson also. So lambda is equal to dq by dl, dq by dl. Now, this dq can be written as lambda dl, and this dl is the arc length. This arc length can be written as radius times angle. Radius times angle. Arc length is equal to r d theta. R d theta. I have got the equation for dq, charge. Now, as I have already mentioned, this is a small charge, a point charge. So we can determine the electric field due to this small charge, which is again small, at this center, at this point. Okay. Now, electric field direction will be in this direction. Okay, this small amount of charge is creating small amount of field at this point, at the center of the arc, now if this angle is theta, this angle also would be theta. This angle is theta, this angle also would be theta. Opposite angles, right? Now, if I, as I have already told you, electric field is a vector quantity, so I am going to divide this vector into two components, two perpendicular components. De theta is in this direction, so de cos theta comes here, and here de sin theta. Here we'll get de sin theta. So here also we have two perpendicular components. The same analysis goes here. The only thing that differs is limits. Okay. Now dex is equal to de x is de sin theta this time, right? And dey is equal to de cos theta this time. De cos theta along y-axis. Now, as I know, let's write the equation for de. Okay, this de. So this is the electric field due to small element charge, which is very small. So I can consider it as a point charge. I'm going to write the electric field due to point charge. De is equal to k dq by let's take the radius of the circular arc as r. Okay, now here comes r square. As I know, dq is equal to lambda r d theta. If I replace it here, k lambda r d theta by r square. 1r cancels and we'll get, okay, this de is equal to k lambda by r into theta. This is the expression that we are going to use in the further equations. Okay. Now let's use it here. Dex is equal to, what is de? K lambda by r d theta. Sorry, here we have d theta. So k lambda by r d theta, we have sin theta here. Okay, let's write the equation here. dy is equal to k lambda by r d theta. We have cos theta here. Are the steps followed here are clear to you? If you have any difficulty in understanding the steps that I'm following, please comment below. Okay, so I'm sure you'll be able to follow the entire analysis, all the steps, entire explanation, as I'm going through the simplest manner or simplest way of solving the things. Okay, solving the concept, solving the questions. Now uh, this is the x component of electric field due to this small element, but I want to find the electric field, x component of electric field due to this entire arc. In that case, I'm supposed to integrate it. So as I know, this entire thing goes like ex. Okay, integral dx is x, so integral dex is ex. Now k is constant, lambda is again constant, r is also constant. Integral sine theta. Sine theta integration is minus cos theta, so I'm taking minus sign here. Sorry, cos theta comes here. Cos theta comes here. Let's use same analysis goes here. Ey is equal to integration k constant, lambda constant, r constant. Cos theta integration is sine theta. Okay, now let's use the limits. Let's use the limit is from minus infinity to plus infinity. Limit is from minus lambda minus alpha by 2 to plus lambda by 2. So the limit is minus alpha by 2 to plus alpha by 2. Minus alpha by 2 to, limit is for angle only, right? So the angle is extended from minus alpha by 2 to plus alpha by 2. Minus alpha by 2 to plus alpha by 2. So minus alpha by 2 to alpha by 2. Minus alpha by 2 to plus alpha by 2. Minus alpha by 2 to plus alpha by 2. Minus alpha by 2 to plus alpha by 2. Now let's substitute the limits. Ex is equal to k lambda by r cos alpha by 2 cos alpha by 2 minus minus cos minus alpha by 2. We have minus sign here, right? Minus k lambda by r x is equal to, right? Minus k lambda by r cos alpha by 2 minus cos of minus theta is cos theta only, because cos is an even function. So cos of minus theta is cos theta. Again I'm writing cos alpha by 2. So this will result in 0. This will result in 0. So the final answer would be electric field along x direction is again 0. Again 0. Hope I made the point clear here. Right? Now let's simplify these steps. Ey is equal to k lambda by r sine alpha by 2 minus sine minus alpha by 2 whole into. Now sine is an odd function. Sine of minus theta is minus sine theta. So Ey is equal to k lambda by r sine alpha by 2 minus how much, plus sine alpha by 2. So as we have sine alpha by 2, the result will be Ey is equal to 2k lambda by r. 2k lambda by r. 2k lambda by r, sorry. 2k lambda by r. 2k lambda by r into sine alpha by 2. Sine alpha by. Okay. So this result is important. This result also important. If you want to find the E net is equal to root over ex square plus ey square is equal to how much? Ey only, because Ex is 0. So Ey is what? 2k lambda by r into sine alpha by 2. Alpha is what? The angle extended by the arc. Angle extended by the arc. So this is the general equation. General equation for the electric field of the circular arc. Circular arc. We can use this formula and for any length of arc. Any length of arc. Okay. Now, what is the final result? E net. E net is equal to 2k lambda by r into sine alpha by 2. Alpha by 2. Alpha by 2. Okay. Right. Let's use this formula and find different sections of ring, sections of find the electric field due to different length of circular ring. Okay, now let us take a semicircular ring like we have discussed. Okay, semicircular ring, let us check whether it is matching or not. Semicircular. Now, for a semicircular ring, total alpha is equal to how much? 180 degrees. Alpha is equal to how much? 180 degrees. Okay. Now, electric field E is equal to 2k lambda by r, 2k lambda by r sine alpha by 2, sine alpha by 2. Alpha is how much? 180 degrees. So 2k lambda by r sine alpha 180 by 2. 180 by 2. 180 by 2 is 90 degrees. Sine 90 value is 1. So what am I getting? 2k lambda by r is the net electric field due to a semicircular wire. When you look at the earlier, case, you'll be able to understand. The final answer, what is E net? Where did we find it? So what is E net? 2k lambda by r. The same answer comes here if you use the general formula. If you use the general formula. Even you can take a quarter circle also. A quarter circle also. If the radius is r and linear charge density is lambda. Now, E net, and this alpha is equal to how much? Pi by 2, which is 90 degrees, which is 90 degrees. E net is equal to 2k lambda by r sine alpha by 2. What is alpha here? 90. So 2k lambda by r sine 90 by 2, which is 45 degrees. Sine 45 value is 1 by root 2. So 2 by root 2 k lambda by r. 2 by root 2 means root 2 comes here, right? So E net is equal to root 2 k lambda by r. Root 2 k lambda by r. Root 2 k lambda by r. This is the net electric field due to a quarter circular arc. Quarter circular charged arc of wire. Okay. So, and one more conclusion I want to give you here. That is, E net is root 2 k lambda by r. That means x component is k lambda by r and y component is also k lambda by r. E net comes out to be Ex square plus Ey square, as both of them are same, so you will get root 2 k lambda by r. Root 2 k lambda by r. By using this one, I have defined the x and y components of the electric field of the quarter circular charged arc. Okay, so you can use the generalized formula of electric field due to a circular arc. E is equal to 2 k lambda by r into sine alpha by 2. Alpha by, you need to remember this formula where alpha is what? Angle made by the arc. Angle made by the arc. Circular arc. Angle made by the circular arc, circular arc, right? Are the examples understandable, right? We will also discuss some of the examples, some more examples to make everything clear on this topic, right? Okay, let's erase entire thing. Let's discuss some more examples on this, circular arcs. Okay, right. Now let's look at one more example. Okay, now I have a circular, semicircular wire here, which is um, which is having positive lambda charge density, positive lambda charge density. Now let us take one more semicircular arc. Sorry, the diagram is not clear here. One more semicircular arc, something like this, and its linear charge density is minus lambda. Let it be minus lambda. Okay. Now radius of both the wires are same, which is r, which is r. Okay. Now what is the net electric field at this point? Which this is the question. E net is how much? E net is how much? I would like to give the magnitude and also the direction. Okay. Right. Direction of the electric field. Now let us take the first semicircle, that is of positively charged. Okay, we have already discussed the electric field due to the semicircular wire. Electric field due to semicircular wire is E is equal to 2k lambda by r, 2k lambda by r. For a positively charged semicircular wire, if I take this one, this is the center, sorry, this is the center. Okay, now the electric field will be in this direction. So electric field due to positive charge, positive lambda, right? Okay. Now this semicircular, wire is providing certain electric field in the downward direction, which is away from the positive charge, away from the positive charge. Now if I take negative charge, negatively charged linear charge density, and the field due to this negatively charged linear charge density at this at this point at this point is towards the charge, de I mean sorry electric field due to negative lambda. As I've already told you, the electric field due to positive charge is always pointing away. Okay, but the electric field due to negative charge is always pointing towards the negative charge, this negative charge is distributed below the reference line, x-axis. That means the field is pointed towards the charge, downwards, and this positive charge is above the x-axis. The field must be pointing away from the charge. When you look at these two, these fields are pointing in the same direction at the point of interest, so the net field is E plus lambda and E minus lambda. Both are pointing in the same direction, then E net must be E plus lambda plus E minus lambda magnitudes. Both of them are acting in the same direction. We already know the electric field due to circular arc is 2k lambda by r plus 2k lambda by r. This is minus lambda, but I have taken the magnitudes because I have already used this diagram and directions. I have already used the direction based on the common sense. I mean, positive charge, electric field due to positive charge is pointing away, electric field due to negative charge is pointing towards. As the negative charge is below the x-axis, pointing towards, which is downwards, as the positively charge density is above the x-axis pointing away, which is again downwards. So both the fields are acting in the same direction, which is downwards. So I have added them directly. Okay, so 2k lambda by r, 2k lambda by r, which is equal to 4k lambda by r is the net electric field at the center. Now look at one more example. Instead of taking two semicircular, rings, I've taken one ring. One ring. One ring. Now, if this is positive lambda, this is also positive lambda. Positive lambda, positive lambda. Now, what is the electric field at the center? At the center, the field due to this one acting in this direction, downward direction, the electric field due to this lower section of the semicircular ring acting in upward direction, as both of them are of same linear charge density, so they gets cancelled out. Hope my point is clear, right? Let's look at one more example. So the electric field E is equal to 0. For a charged ring, the electric field at its center is 0. Now let's look at one more example. Okay, let's look at one more example. Now, what I'm going to consider is, okay, now this is circular arc, okay, and this is another circular arc, and this is another circular arc, this is another circular arc. These are all circular arcs, 4 circular arcs that I have taken, and I'm going to represent the charge densities. Linear charge density of this one is plus lambda, this is also plus lambda. Circular arcs, quarter circle, okay. Now linear charge density plus lambda, and linear charge density of this one is plus lambda, and this one is minus lambda. Okay, now the question is asked to find the net electric field at this location. E net is equal to how much? Okay, E net is equal to how much? Okay, sorry, E net is equal to how much? Okay, E net is equal to how much? Now let's find that out. Okay, now as we all know, the electric field due to this quarter circle will be in this direction. Okay, and the electric field due to this section, I'm taking it as 1, 2, 3, 4. Electric field E1 is in this direction, and electric field E3 will be in this direction. This E1 is nothing but root 2 k lambda by r, we have already determined, and this is also root 2 k lambda upon r. Two equal amount of fields acting in opposite directions, so they cancel out. That means the net field along this direction is 0. Okay, now coming to the next case. Now, as this is minus lambda, the field due to this semicircular, not semicircular, quarter circular arc is towards the quarter circular arc, towards the negative charge. This is E2, which is equal to k root 2k lambda by r, in this direction. And again we have left with fourth quarter circle. The fourth quarter circle is positively charged. The field due to this fourth quarter circle will be in the same direction, as that of this one. Okay, this is E4 is equal to root 2 k root 2 k lambda by r, So what is the net field? E net is equal to E2 plus E4. E2 plus E4. If I add both of these, what am I getting? 2 root 2 K lambda by R. This is our final answer. This is our final answer. Hope the examples that I have discussed so far are very clearly understandable, right? If you still feel difficulty in understanding, please comment below. I'm suggesting or requesting you to watch the videos not for once, at least for two times, at least for two times, so that you will be able to grab the entire analysis, you will be able to understand the entire concept, and you will be able to apply the concept that you have learned in the videos. Okay, so so yes, these are the examples that are related to circular, semicircular, quarter circular, and a common circular arc related examples and the problems as well. Okay, now let's move ahead and discuss one more example. Okay, this is a very good concept. The questions have been asked based on this concept, from this concept actually, in uh, in competitive exams such as mains, NEET, okay, etc. Now now the concept is we need to find the electric field at a point on the axis of the charged ring. So this is the charged ring. This is the charged ring. So this is the charged ring. Let us say the charge on the ring is Q. Charge on the ring is Q. Even you can take lambda as well. You can take lambda as well. I'm taking Q. Okay. Okay. Now now, as per the title, I need to consider a point on the axis. So I'm going to consider the point somewhere here on the axis of the ring. Axis of the ring. The ring is positively charged. Even if you can take negative charge as well, but however, the direction of the electric field opposite to the positive charge case. Okay, right. I've taken this point. Let this point be P. Point be P. What is this point? P. Okay, now what I'm going to do is, let us suppose the distance to this point from the center is x. From the center is x, and I'm going to consider the radius of the ring is r. Radius of the ring is r. Now I'm going to divide this ring into small elements, small tiny charges. So let us consider a tiny element somewhere here. So this is the tiny element that I have considered. The length of this element is dl. Charge on this element is dq. Charge on this element is dq. So this is a small charge, a small element. Size is very small. So I can consider this small charge as a point charge. As a point charge. The electric field due to this point charge, at the point of interest will be in this direction, DE. As the charge is very small, it is creating small amount of field here. Small amount of field here. It should be a straight line, right? Small amount of charge here. Now, element to point distance that I am considering as R. What is it? R. Now this R can be written as, from this right angle triangle, R can be written as R square plus X square under root. Are we clear? Are we clear? Right. Now, okay. Now, as I've already told you, I've been telling you multiple times, electric field is a vector quantity, so we have to add them vectorially. To do so, I'm going to divide this electric field into two perpendicular components. So one component goes here, other component comes here. Now let us take this angle is theta. This angle is, if this angle is theta, then this angle also should be theta. Now DE component to this direction is dE cos theta. dE cos theta. Now component of this electric field to this direction is dE sin theta. dE sin theta. We have divided this electric field due to this small element into two perpendicular components. Their respective directions are dE cos theta along x-axis, dE sin theta is along y axis. Okay, I am going to consider this as x component, this as y component. Is that okay? Right. Okay. Now let's use our basic common sense of symmetry and analyze this situation little further. Okay. Now similar type of element, because I'm dividing this entire ring into small tiny piece of charges. So this is the element, next is the element, next is another element, another element, and here we have another element, right? Similar type of element, right? Now this element also causing certain amount of field like this amount is also causing certain this amount is also causing certain amount of field in this direction d, right? Now it can also be split into two perpendicular component. One component comes here de cos theta and other component comes here de sin theta, right? I'm going to draw the line here. Hmm, draw the line here. Okay, so d, multiple colors are coming, I don't know why. D, and this dE is resolved into two components, dE cos theta and dE sin theta. When you look at this diagram, these components, here we have dE cos sin theta, here also we have dE sin theta. Can we cancel these two components as they are acting in opposite directions with same magnitude? We can definitely cancel these two components. That means we can come to a conclusion that all the components which are coming along the vertical line are being cancelled out. Look at me. Observe the diagram and imagine a three-dimensional picture of this situation. I've taken a ring. I've taken a ring. Here we have a ring, right? Here we have a ring, this big ring. And the axis is passing through the center. Axis is passing through the center. At the top, I have taken a small element. I've taken a small element, and the electric field due to the small element is in this direction. And now this electric field is resolved into two components. One component comes along the axis, one component goes down. One component goes down. Similar type of component, if you take here, if you take here, somewhere here, let it be somewhere here. Okay, if you take here, this is the ring. If you take another component, the point is somewhere here along the axis, component is here along the axis. Now if you draw a line, the electric field acts in this direction. Now this electric field can also be resolved into two components. One component goes along the axis, other component goes perpendicular to the axis, right? Similar type of opposite component will also be observed somewhere here. Okay, if you, this is the ring that I have considered. I've taken one element here, another element here, I've taken another element here. This time the electric field will be in this direction. If I resolve this electric field into two components, one component goes along the x-axis, other component goes perpendicular, right? One component is going into that direction, another component is going into this direction. These two will get cancelled. Okay, right. So opposite components are being cancelled. The components which are perpendicular to the axis of the ring are being cancelled. What are the components that are being added up, which are acting along the axis of the ring? So these components are not giving any kind of electric field at this point. Rather, these components are giving the net electric field at this point. My point clear to you, right? Okay, let's move ahead. Okay, so the net electric field de net is equal to de cos theta. Okay, so I'm going to take this as e net e net e net e net and I'm going to take the integration to find the net electric field de cos theta. We don't know de at de. First, de is equal to, as I've already told you, this is a small element. The electric field due to small element can be considered as electric field due to a point charge. So de is equal to k dq electric field dE is equal to k dq by, what is the radius? I mean, not the radius. What is the distance between this, a point charge and this point, which is r square, which is r square. It is wrong to use this capital R. It is correct to use this small r, because the point charge is here, teeny tiny charge, and the point that I am finding the electric field is here. The distance between these two is r. So it is always right to take r square, small r square, not the capital R square. Radius of the ring is, if I take radius of the ring square, is it gives wrong results. We need to take the point charge and the point of interest distance, which is r square. And okay, now k dq by r square, k dq by r square. Now what I'm going to do is dE is equal to k dq by r square. What is r? What is r? R is nothing but small r square plus capital R square. R is nothing but small r square plus, r is nothing but small r square plus, capital R square plus x square under root whole square. Right? Okay. Now let us find E net. Now E net is equal to integral dE cos theta. dE cos theta. As I know dE, what is dE? K dq by r square plus x square, square and root will get cancelled. I'm leaving like this. Now what is cos theta? From this triangle, here we have this triangle, from this triangle, cos theta is equal to adjacent upon hypotenuse. So adjacent is x by hypotenuse is smaller, Can I replace this smaller with root over capital R square plus x square? Yes, I can. Capital R square plus x square. I have the integration here. Is my point clear? Right? Okay. Now I'm taking all the constants outside. Now let us identify the constant. K is a constant, which is clear, right? What about x? Is x changing for any of the element? It is again same. This element x is same. This element x is again same. This element r x is same. R is also not changing. Small r is also not changing. X is also not changing. So capital R, small r and small x are all constants. So x is constant. I'm taking x here. R square x square plus r square plus x square. I can write r square plus x square. This is power 1. This is 1 by 2. This would be 3 by 2. Sorry. This would be 3 by 2. This would be 3 by 2. Okay. Kx r square plus x square whole to the power 3 by 2. This is 1. This is 1 by 2. 1 plus 1 by 2 is 3 by 2. And I'm still left with integral dq. Integral dq. Only variable that left is dq. This entire, integration will give out total charge q. Total charge q. So I can write the net electric field as E net is equal to k q x upon r square plus x square whole to the power 3 by 2. This is a very important result, which is the required electric field at a point on the axis of a charged ring. Okay. So many questions have been asked from this concept. Okay, right. Now, so this is a very good result, which is to be remembered. K q x by x square plus r square, or r square plus x square whole to the power 3 by 2, where r, capital R, is the radius of the charged ring, x is the distance to the point on the axis of the ring from the center of the ring. Okay. Now q is the charge of the ring, x we have already defined. K is Coulomb's constant, the value of which is already known, 9 into 10 to the 9, or 1 by 4 pi epsilon naught. Okay. Okay, is the entire analysis is understandable, right? Right. Now, okay, now let us discuss some cases. Some cases. I'm going to take off all this analysis here. Okay, let us discuss. I'm going to write the formula here. E net. E net is equal to K Q X upon R square plus X square whole to the power 3 by 2. Whole to the power 3 by 2. Okay. Now let us take the case. At the center of at the center of ring. At the center of ring. At the center of ring means x would be 0. X would be 0. This is our ring and this is the point. This is the distance x. Right? Now I'm dealing with the point which is at the center of the ring. That means this is our point, right? This is our point, center of the ring. That means x value will be 0. If x is equal to 0, then E net should be equal to 0 because this x value, I'm going to write the entire equation here. So this x value k q x by r square plus x square whole to the 3 by 2. As we have x in the numerator which is 0, which results in 0. So electric field at the center is 0. Now let us look at the other case. Second one. At a very large distance. Very large. At very large distance. From center of ring. Center of ring. From center of ring. That means x is greater than very much greater than r. X is very much greater than r. If very large distance in the sense, at very large distance in the sense, x is very much greater than r. X is very much greater than r. Now I'm going to use the same equation. If x is very much greater than r, then r square can be neglected. R square can be neglected. Let us suppose x square is resulting 100, r square is 0.1. That means the sum of both of them, 100 plus 0.1 is 100.1. If I round up that value, it will give 100 only, right? Right? It is a basic common sense point. So I can write this E net is equal to K Q X upon X square whole to the power 3 by 2. Now 2 will get cancelled, 1x will get cancelled, k q by x square. So this is the equation for the electric field due to point charge. Electric field due to point charge. So if the ring is here, if I go farther distance from the ring, when compared to the radius of the ring, this x distance is very large, then this ring will appear as a point charge. That is the reason we have got the electric field due to point charge result here. Okay, this is the second case. When we look at the third case, let us look at third case. Okay, point is at infinity, or I can simply write it as at infinity. At infinity. At infinity. At infinity. At infinity, x would be infinite. X would be infinite. If x is infinity, then I place x is equal to infinity. What am I getting? If x is equal to infinity, this entire thing will be infinity. Infinite. Anything. In the denominator we have infinity means the net electric field at infinity is 0. Net electric field at infinity is 0. Okay. So when you look at the results at 0, that means at the center it is 0, at infinity also 0. In between these 2 points, somewhere this ring will appear as a point charge, and from these 3 results, I can conclude that the electric field may be maximum in between center of the ring to infinity. Center of the ring to infinity. Let us find where the electric field is maximum along the axis of the charged ring. Along the axis of the charged ring, we will also find the maximum possible electric field due to this charged ring along the axis. Along the axis. Now, along the axis. Okay. Now, I'm going to take this entire thing off. Okay. Right. I'll keep only the formula. Okay. Now, now. Okay. Now, let's use the same formula. Okay. Now, so for for E to be maximum, E to be maximum, maximum, the differentiation of electric field with respect to x must be what? 0. Why we are differentiating this electric field with respect to x, not with respect to capital R, not with respect to any other term, because we are measuring the electric field with respect to the position only, with respect to the distance from the ring only. That is the reason I've taken this electric field, differentiation of electric field with respect to the position or the distance from the center. Right, dE by dx is equal to 0. And why we have taken this dE by dx is equal to 0? Because whenever the electric field is maximum, its differentiation should be equal to 0. Whenever the electric field is minimum, then also the differentiation, first order differentiation, should be equal to 0. So this is the case that I am using here. dE by dx is equal to 0. Now d upon dx, what is electric field equation? K q x by r square plus x square whole to the 3 by 2, whole to the 3 by 2. This is the equation that I mean that we need to differentiate with respect to x, which should be equal to 0. K is constant, q is constant. I'm taking k and q outside of the differentiation. We have x on the numerator, r square plus x square whole to the power 3 by 2 is on the denominator. Both the terms are of function x, so we need to use u by v method. U by v method. If you have learned this differentiation in the first year, 11th standard, you will be able to follow it. If you have not learned the differentiation yet, please check out the formulas of differentiation and come back here and learn it again. So use u by v method of differentiation, of differentiation u by v method of differentiation. Okay, now let's use u by v method. What is u by v method? U by v method formula. So d by dx of u v is equal to v into du by dx minus u into dv by dx whole by v square, whole by v square. Okay, clear? This is the formula that we are going to use to find to differentiate this equation. Now what is u here? X. What is v here? R square plus x square whole to the power 3 by 2. Okay, now v in the denominator we have v square, in the denominator we have v square, so r square plus x square whole to the power 3 by 2 whole square, whole square. Keep it as it is. Now v r square plus x square whole to the power 3 by 2, whole to the power 3 by 2, d by dx of u, d by dx of u is how much? X. U is x. I've taken the constants k and q outside. K q, k q. Are you following the steps or not? Okay, so because we are dealing with the calculation, so I am going little slowly. Okay, right. Right, now let's move on to the next step. Minus u is x, u is x, and dv by dx, d by dx of what is v here? It is r square plus x square whole to the power 3 by 2, whole to the power 3 by 2. Right, now let's differentiate, which is equal to 0, which is equal to 0. Right, now simplify. If I take this kq to this side, it will become 0. Now let's keep r square plus x square whole to the power 3 by 2. And I forgot to tell you, if I take this k cube to this side, it will be 0. If I take the entire denominator to this side, it will also be 0. It will also be 0. So r square plus x square whole to the power 3 by 2 dx by dx is nothing but 1. Nothing but 1. Now minus x and differentiation of this one. Differentiation of x to the power n is n into x to the power n minus 1, 3 by 2 minus 1. N into x to the power n minus 1. Okay, this is not x. We have the function x here. So the chain rule also applies. So if we use the chain rule, we have to differentiate this inner function as well. So differentiation of 2x, x square is 2x, right, is equal to how much? 0. Is equal to 0. Now here we have r square plus x square whole to the power 3 by 2, 3 by 2 minus, we have 3 by 2 here, 2 will get cancelled, we have 3 here, we have 3 here, right, 3 x into x square, 3x square, r square plus x square whole to the power 1 by 2 is equal to how much? 0. Now I have this r square plus x square whole to the power 3 by 2 means whole to the power 1 plus 1 by 2. I can take r square plus x square whole to the power 1 by 2 as common. What do we left with? R square plus x square whole to the power 1. Whole to the power 1. I am not writing the 1 here because we already know. Minus 3x square, because this is already taken common, which is equal to 0. Whatever the value you take for x, this entire term will not be equal to 0. Will not be equal to 0. So this term will not be equal to 0. So the only term that is possibly can be equal to 0 is this one. This will be equal to 0. If I equate this entire term to 0, what do we left with? R square, x square minus 3x square is minus 2x square is equal to 0. Is equal to 0. What is x value? Plus or minus r by root 2. Very, very, very important result. At this position along the axis of the rod, the electric field is maximum. At this point the electric field is 0. At this point the electric field is maximum, and at infinity it is again 0. Right? In between center and infinity there is some point where the electric field is maximum, which is x is equal to r by 2. X is equal to r by root 2. R by root 2. Is my point clear? Right. Let's move ahead. Let's find at this position. We have identified that, we have determined that at this location the electric field is maximum. Now what we are going to do is, we are going to find what is the maximum electric field possible. Let's find the maximum electric field. Okay. Let's clear this entire thing. I'm going to write the equation. E net is equal to k q x by r square plus x square whole to the power 3 by 2. As we know, for E max x should be plus or minus r by root 2. Now for E max we need to substitute this value for x. K q x is r by root 2 by r square plus r by root 2 whole square whole to the power 3 by 2. Let's simplify this one. Okay. Now k q r by root 2 by, this is r square, r by root 2 whole square, in the sense r square by 2, we will get 3r square by 2 whole to the power 3 by 2. whole to the power 3 by 2. Now, if I rewrite this equation, k q r by root 2 by uh, r by root 2, okay. Now r square, this will be square, 2 will get cancelled, we will get r cube here, and 3 power 3 by 2, which is 3 power 1, 3 power 1 by 2, that means 3 root 3, 3 root 3, and we have 2 to the power 3 by 2 in the sense 2 root 2, 2 root 2, see, 3 power 3 by 2, 3 by 2, that can be written as 3 to the power 1 into 3 to the power 1 by 2, 3 to the power 1 plus 1 by 2 is 3 by 2, right? So 3 power 1 is 3, 3 power 1 by 2 is root 3. Similar steps goes for 2 to the power 3 by 2 also, which is in the denominator, so 2 root 2, 2 root 2. Here we have root 2, here we have root 2, both will get cancelled. Okay, now what do we left with? E max, E max is equal to, this 2 goes to the numerator, 2 k q by 2k q by 3 root 3 into r cube, r cube, r cube, r cube. We have one r here, that is sorry, we have one r here, that also goes out, so we will get what we will get, we will get r square, we will get r square, 2kq by root 3 r square is the maximum possible electric field at a distance, at x is equal to plus or minus r by root 2, r by root 2, r by root 2. Hope the point is clear. I am going to draw the diagram. So this is the ring that I have considered. Now the axis is this one on both sides, right? Now the point, this is r, and this is at a distance r by root 2, which is positive, and this is again a distance which is minus r by root 2. On both sides of the ring there is a possibility, there is a maximum electric field possible, maximum electric field possible. That maximum electric field is 2kq by 3 root 3 r square. If we are measuring the electric field along positive x, it has to be taken as positive. If we are measuring the electric field in the negative x direction, it has to be taken as negative at the same distance, r by root 2 minus r by root 2, right? Now let's move ahead and draw the graphical representation of the electric field, okay, which is an interesting thing. So this is the ring, this is the y axis, and this is the x axis. Okay, x on y axis I have taken electric field, okay. Now, right, I've taken electric field. Now this is the center, and this graph can also be extended to the negative x axis, negative y axis as well. Okay, right. Now let us analyze this equation. Electric field at the center, is 0. That means graph should begin here, now as we move away from the center, the electric field keep on gradually increases, right? Gradually increases as per this equation, so gradually increasing, okay, sorry, gradually increasing, okay. Now at some point the electric field will be maximum. That distance is nothing but plus r by root 2. And after that what happens? It again gravitation, I mean the electric field again decreases. And it becomes 0 at infinity. 0 at infinity. 0 at infinity. Okay, 0 at infinity. That is the reason infinity is somewhere far away from the ring. So I haven't touched this graph to the x-axis. We don't know where it is becomes 0. So same graph along the negative x-axis. As I've already told you, if you are measuring the electric field along the negative x-axis, the electric field is to be taken as negative, because electric field is a vector quantity. It also the direction also represented along with the magnitude. Okay, so direction negative x, negative e, while we are going for negative x direction. Okay, as it is also starting from the center, and the electric field gradually increases, and it becomes maximum, maximum at some point, and it will be infinity, it will be 0 at infinity, 0 at infinity x, it will be 0 at infinity. So this is the E max negative, this is the E max positive. Okay, this is the distance plus r by 2, and this is the distance minus r by root 2, plus r by root 2 minus r by root 2. This is the graphical representation of the electric field along the axis of a circular charged ring. Okay, the maximum electric field is possible at a distance r by root 2, and that maximum electric field is 2k cube by 3 root 3 r square, It is a very good concept. I hope you have understood the entire steps, entire concept, entire explanation that I have followed through. So if you find the videos helpful, please do like, share, subscribe, and don't forget to hit the bell icon in order to get the notifications as soon as I upload the videos. So that's it in this video. See you in the next video.